Texan Global School. Ellipse. In this class, different forms of the ellipse equation are analyzed. By definition, an ellipse is a locus of a point in the plane, such that the sum of their distances to two fixed points on that plane is always equal to a constant greater than the distance between the 2 points. We can see that F and F' are the foci. L is the focal axis, which is the straight line that passes through the foci. V and V' are the vertices. The focal axis cuts the ellipse at these 2 points. The distance between these points is the major axis, which is the portion of the focal axis included between the vertices. C is the center, located on the focal axis, which is the midpoint of the segment that joins the foci. Or it is also the midpoint between the vertices. L' is the normal axis, which is a line that passes through the center and is perpendicular to the focal axis. The minor axis is the portion of the normal axis included between the points A and A'. A chord B and B' is a line segment that joins any 2 points of the ellipse. E and E' is the focal chord that passes through one of the foci. The lattice rectum L and L' is a focal chord perpendicular to the focal axis. We see that the ellipse has 2 straight sides since it has 2 foci. A diameter D, D', is a chord that passes through the center, and FP is the focal radii, which is a straight line that joins the focus and any point on the ellipse. We will obtain the first standard equation of the ellipse. We will consider an ellipse with center at the origin and a focal axis coinciding with the x-axis, t. Fo F and F' are on the x-axis, t. These points can be defined as C, 0 and negative C, 0, where C is a positive constant that represents the distance from the center to the focus. T. The vertices are the ends of the longer side, and they are at the points A, 0 and negative A, 0. W. Here A represents the length of the semi-major axis, A, and the ends of the minor axis are 0, B and 0, negative B. Here B represents the length of the semi-minor axis. If we define any point on the ellipse, P of coordinates x, y, by definition of ellipse, the sum of their distances to 2 fixed points on the plane is always equal to a constant greater than the distance between the 2 points. Algebraically, this definition can be expressed as the distance f, p, plus the distance f', p equal to 2a, where a is a positive constant greater than c. By obtaining the distances between the foci and the defined point and substituting them into the equation, we obtain the square root of x minus c squared plus y squared plus the square root of x plus c squared plus y squared equal to 2a. Ding the second term to the right side. Expanding and simplifying, we obtain c x plus a squared equals a times the square root of x plus c squared plus y squared. Airing, developing, and simplifying results the equation a squared minus c squared times x squared plus a squared times y squared equal to a squared times a squared minus c squared. Sign ca is a positive constant greater than c, then a squared minus c squared will also be a positive number, which we will define as b squared. Then obtain the relationship of b squared equal to a squared minus c squared. When substituting, we have x squared by b squared plus a squared by y squared equal to a squared by b squared. If we divide the entire equation by a squared, b squared, and simplify, we obtain the simplest form of the equation of an ellipse, called the first standard equation or canonical form of an ellipse, when its center is at the origin and its axes coincide with the coordinate axes. If we discuss this equation of the ellipse, we will start with the intercepts with the axis, L. At US, remember that the intercepts with the x-axis are obtained when y is equal to 0. S. O. The intercepts with the x-axis are the vertices of the ellipse, and the length of the major axis is the constant defined as 2a. N. O. The intercepts with the y-axis are obtained when x is equal to 0. T. Herefore, the intercepts with the y-axis are the points 0, b and 0, minus b. Therefore, the length of the minor axis is 2b. The next point of discussion is symmetry. Symmetry with respect to each axis is analyzed by replacing y with minus y and then x with minus x. In general, the ellipse is symmetrical with respect to both coordinate axes and also with respect to the origin. Now, to determine the extent of a curve, isolate each variable and analyze. F. or the determination of the variation intervals for which x are real numbers, that is, the domain, by solving for y, so that the domain includes all real numbers greater than or equal to negative a and less than or equal to a. T had as all values within the major axis a. ND for the determination of the intervals of variation for which y are real numbers, range, by solving for x. Hence, the range includes all real numbers greater than or equal to negative b and less than or equal to b. T had as all the values within the minor axis f, or the asymptotes. Also analyze the isolated variables. The ellipse is limited by the lines x equal to plus minus a and y equal to plus minus b, thus showing that it is a closed curve. Therefore, it does not have vertical or horizontal asymptotes. Using again the first standard equation of an ellipse, from its foci it can be seen that C is the abscissa. If we use the equation of the ellipse with the y cleared to obtain the value of the ordinate, substitute C with x, and, using the previous relationship between a, b, and c, results that the ordinate is b squared over a. S value is the length of the ordinate or focus to a point on the ellipse perpendicularly. Therefore, the length of the latus rectum will be twice that distance, as shown on the board. Fin, ally, eccentricity is the measure of how much a conic section deviates from being circular. In a circle, the eccentricity is 0. Therefore, the eccentricity E is given by the ratio C over A, and using the same relationship between the variables, we see that the eccentricity of the ellipse is represented as the square root of a squared minus b squared over a. This value must be less than 1. If we now consider an ellipse whose center is at the origin, but its focal axis coincides with the y-axis, T, foci f and f' are on the y-axis, whose points can be defined as 0, c and 0, negative c, where c is a positive constant that represents the distance from the center to the focus. T, vertices ends of the longer side are at 0, a and 0, negative a. A, and the ends of the minor axis are b, 0 and negative b, 0. W, if the same process, results that the equation of the ellipse is the same, but with the variables a and b inverted. The summary of the derived formulas is shown on the blackboard, which is very important to have on hand to solve the problems. The first standard equation of the ellipse is shown, centered at the origin, as well as all the elements to be able to analyze it. Let's look at an example. Find the equation of the ellipse whose foci are the points 2, 0 and negative 2, 0, and its eccentricity is 2/3. Analyzing the given foci, we can see that they are located on the x-axis, and since the foci are at c, 0 and negative c, 0, hence c is equal to 2. And since c represents the distance from the center to the focus, the midpoint between the foci is the origin. Because the given eccentricity is 2/3 and is the quotient c over a, it is confirmed that c is equal to 2, and results that a is equal to 3. Now, since the vertices, or extremes of the longer side, are at a, 0 and negative a, 0, then the vertices are at 3, 0 and negative 3, 0. Using the relationship between a, b, and c, substitute a equal to 3 and c equal to 2 to obtain b. So b is equal to the square root of 5. We then have that the ends of the minor axis, given as 0, b and 0, negative b are the points, 0, square root of 5 and 0, negative the square root of 5. And since a is equal to 3 and b is equal to the square root of 5, the equation of an ellipse with center at the origin and focal axis on the x-axis is x squared over 9 plus y squared over 5 equals 1. And d, then, we can calculate the length of the latus rectum by substituting the variables. In this case, it is 10/3. See all the elements are obtained. Let's graph. So, by solving for y, we can see that the domain is from negative 3 to 3. Any value proposed outside this domain will give some value outside the set of real numbers. So the tabulation confirms that the vertices are at 3, 0 and negative 3, 0. The ends of the minor axis are at 0, plus minus square root of 5. On the other hand, if the coordinate axes are moved to a new origin of coordinates h, k, the new parallel coordinate axes will be x' and y', thus generating new coordinates. Then, the transformation equations from the old system to the new coordinate system are x equals x prime plus h, y equals y prime plus k. Considering then an ellipse with center at the origin, an axis coinciding with the x-axis, let us perform a translation of coordinate axes. The coordinate axes can be moved parallel to a new origin h, k. The new parallel coordinate axes will be x prime and y prime, generating new coordinates. Then, the equation of the ellipse referred to the new coordinate system is shown on the blackboard. Performing the translation of coordinate axes, substituting, results the equation of an ellipse when its center is at the point h, k, and its focal axis is parallel to one of the coordinate axes. This is the second standard equation of an ellipse. The summary of the derived formulas is shown on the blackboard. We can see that the coordinates of the foci, vertices, and so on are specified according to the new origin h, k. T, key relationship between A, B, and C, the latus rectum, the length of the straight side, and the eccentricity do not change. Hey are the same derived formulas. Let's look at another example. The foci of an ellipse are the points 3, 8 and 3, 2. The length of its minor axis is 8. Find the equation of the ellipse, the coordinates of its vertices, and its eccentricity. We can see that the foci are not on the x-axis nor on the y-axis. Therefore, a second standard equation of the ellipse will be obtained. Because the foci are the points 3, 8 and 3, 2, the center can be obtained since it is the midpoint. So when applying the formula seen in previous classes, the midpoint, in this case the center h, k, is 3, 5. Since the length of the minor axis A, prime A of the ellipse is 8, and we know that B is the length of the semi-minor axis, then B will be half of the minor axis. In this case, equals 4. Now, since C is a positive constant that represents the distance from the center, 3, 5, to any of the foci, we can use the formula to obtain the distance between 2 points seen in previous classes. By substituting the values of the center and any of the foci, results a distance of 3, which represents the value of C. Since we already have the values of B and C, use the relationship between A, B, and C. By substituting values into the equation, results that A equals 5. And since the foci are on the major axis, and it is parallel to the y-axis, and with the coordinate of the center h, k equal to 3, 5, we can obtain the equation by substituting into the second standard equation of an ellipse. Results the equation x minus 3 squared over 16 plus y minus 5 squared over 25 equals 1. Likewise, we can obtain the length of the latus rectum. In this case is equal to 32 over 5, and the eccentricity is 3/5. With all values of A equal to 5, B equal to 4, C equal to 3, H equal to 3, and K equal to 5, we can obtain the coordinates of the vertices as well as the ends of the minor axis. The vertices are located at the coordinates 3, 10 and 3, 0. The ends of the minor axis at 7, 5 and -1, 5. It is not necessary to learn the formulas. As the ellipse is being graphed, these coordinates can be deduced. Using those same values, it is verified that the given coordinates of the foci are correct. Let's look at the graph of this ellipse. As mentioned before, it is not necessary to learn all the formulas. You can deduce the elements as you find them. For example, the direct equation shows the center at 3, 5, A. ND, the denominators define the values of A and B, depending on whether the ellipse is horizontal or vertical, as in this case. T, key center vertices and foci are on the same axis. Rom there, the abscissa or ordinate can be defined as the case may be. And the ends of the minor axis are aligned to the center of the ellipse. T, key formulas are shown with all the elements to compare and verify their graph. On the other hand, let us find the general form of the equation of an ellipse. It can be done by algebraically developing the second standard equation. Begin by multiplying by a factor that eliminates the denominators, which is the least common multiple. By multiplying each term on both sides of the equation, the denominators are eliminated. So develop the squared binomials as perfect square trinomials, remembering the class of special products, and again, multiply each term by the external factor. By grouping, assign variables to each group of terms displayed on the board, thus obtaining the general form of the ellipse equation. Conversely, if we complete squares to the general form, the standard form is obtained. Let's remember the methods seen in previous classes. First, in case the numerical coefficient of the quadratic terms is different from 1, multiply both members of the equation by their multiplicative inverse to make them 1. In this case, multiply by 1 over AC. Now send the independent term to the right side of the equation, and then group. Hence, factor to begin assembling the perfect square trinomial, leaving the quadratic term with a coefficient equal to 1. Then, multiply the numerical coefficient of the linear terms d and e by 1/2 and square the result. Then, add the values obtained on both sides of the equation. But beware that in order not to alter the equation, each value must be added multiplied by the common factor that we did in the previous case. If it is not done this way, the equation is being altered. So two perfect square trinomials are obtained. Factor each perfect square trinomial as a square of a binomial, and then develop the equation. If we define m as that part of the equation, we can adapt it to obtain the second standard form of the equation of an ellipse. We will use the previous example to obtain the general and standard form of the ellipse. First, develop algebraically by multiplying by the least common multiple of the denominators to eliminate them. In this case, multiply by 400. By multiplying each term by 400 on both sides of the equation, results that the denominators are eliminated. Then develop the squared binomials and the products. By grouping, we obtain the general form of the ellipse equation. 25x squared plus 16y squared minus 150x minus 160y plus 225 equals 0. Conversely, using this same equation in general form, if we complete squares, the standard form is obtained. Since the numerical coefficients of the quadratic terms are different from 1, the method suggests multiplying both members of the equation by the reciprocal of the least common multiple of the numerical coefficients of the quadratic terms to make them 1. Nevertheless, it is not necessary since the process will add more steps. Directly send the independent term to the right side of the equation, and group also obtaining a common factor to begin assembling the perfect square trinomial. Now multiply the numerical coefficient of the linear terms, -6 and -10, by 1/2 and square each result. The values obtained are added to both sides of the equation. Remember that in order not to alter the equation, you must add, on the right side, each value multiplied by the common factor. In this way, two perfect square trinomials are obtained and the equation is not altered. Factor each perfect square trinomial as a square of a binomial. So the equation is developed, obtaining the same second standard equation of the ellipse seen in the previous exercise.
Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com